mission underway. Vital to its success and to the success of all missions is the aviator's thorough understanding of basic weather phenomena, among them pressure systems and related winds. As a beginning, let's consider pressure, the result of the air's weight. At the bottom of the atmosphere, sea level, the pressure is greatest, with a standard value of 29.92 inches of mercury. It decreases with a gain in altitude. Because of this correlation between altitude and pressure, the altitude of an aircraft may be determined by measuring the pressure. Pressure changes in the horizontal plane because the Earth is unevenly heated. Since the Earth's temperature is constantly changing, the density of the air above the Earth is also constantly changing. This unceasing pressure change is one of the basic factors in weather. As a result of uneven heating, there is a theoretical primary pressure and wind circulation pattern set up in the Earth's atmosphere. The intense heating and convergence near the equator causes the air to rise, creating a low-pressure belt that extends around the Earth's surface in that region. Some air cools and descends near 30 degrees north latitude. Some continues to the polar region and descends. As a consequence, higher pressures are built up in both of those general areas. However, at 60 degrees north latitude, polar air moving southward over the Earth converges with the warm air moving north. The warmer air rises and results in relatively lower pressures in this vicinity. Pressure and pressure changes are measured with barometers. The mercurial and aneroid are the types commonly used. The value of the pressure is expressed simply as the height of the column of mercury in the tube. The same unit has been adopted on aneroid types. Thus, standard pressure at mean sea level may be expressed as 29.92 inches of mercury. Another measuring unit is the millibar. 29.92 inches of mercury is equal to 1013.2 millibars. It would be well to remember that all pressure values on the surface weather map are corrected to mean sea level. For example, the pressure at Missoula, Montana is 1032.9 millibars. Huron, South Dakota is 1026.1 millibars. Terre Haute, Indiana is 1011.2 millibars. And Hatteras, North Carolina is 1023.0 millibars. By measuring the pressure at numerous points over a large area, we can produce a picture of pressure systems as they may exist at any particular time. Let us examine a significant feature of all weather maps, the configuration of lines called isobars. Simply stated, isobars are lines drawn through points of equal pressures. This data comes from weather stations and other sources. Isobars, then, will show areas of relatively high and low pressures. The relative pressures of these systems are indicated by a blue H for high, a red L for low. Though spacing of isobars may vary depending on the scale of the map in use, one common interval employed is 4 millibars. The change of pressure per unit of horizontal distance is called the pressure gradient. In this area, the pressure has changed 4 millibars over a 100-mile distance on the horizontal plane. The pressure gradient, then, in this area is 4 millibars per 100 miles. Stated more precisely, the pressure gradient is the change of pressure with distance from high to low and perpendicular to isobars. It follows, then, that isobars spaced closely indicate a strong pressure gradient. And conversely, isobars spaced widely on the map indicate a weak pressure gradient. It can be stated, then, that closely spaced isobars, or a strong pressure gradient, are more closely associated with low pressure areas and relatively strong winds, while widely spaced isobars, or a weak pressure gradient, are more closely associated with high pressure areas and lighter winds. Pressure patterns are frequently elongated and produce a pressure ridge or pressure trough. Frequently, but not always, cold fronts and warm fronts with their associated weather lie along these troughs. As fronts and pressure systems move, the pressure changes. The nature of the change and degree of change is reported by weather stations as the pressure tendency. This station shows a current pressure of 1017.4 millibars, and during the past 3 hours, the pressure has been falling steadily. The amount of change in the last 3 hours was a decrease of 1.2 millibars. Analysis of this tendency is important to the meteorologist in forecasting the weather. We have been talking about pressure changes on a horizontal plane. Measured vertically, pressure changes are much greater. It will be noted that with altitude, the rate of pressure decrease diminishes rapidly. By the time an altitude of 18,000 feet has been reached, the pressure has decreased approximately 50%. Let us see how the vertical pressure gradient varies with the temperature within the column of air. In the standard atmosphere, the 850 millibar level is at 5,000 feet. And the 700 millibar level is at an altitude of 10,000 feet. In cold air, the density of the air is increased and the isobaric surfaces are lower. Thus, the vertical pressure gradient is increased. In warm air, the density of the air is decreased and the isobaric surfaces are higher. Thus, the vertical pressure gradient has decreased. Because of this variation in the vertical pressure gradient, there is an error in aircraft altimeters called temperature error. Correctly set, the altimeter only indicates the true altitude when the vertical temperature and pressure distribution are standard. In air colder than standard, the aircraft is lower than the indicated altitude. In warm air, the aircraft is higher than the indicated altitude. Aviators do not attempt to adjust their altitude to correct for this, but should be aware of it. In instrument flight conditions, if flying at the minimum instrument altitude, you should request a higher altitude assignment from air traffic control. Altimeter errors also result from failure to correct for the pressure change over the flight routes. If a pilot flies into lower pressures without resetting his altimeter, his aircraft is lower than the altimeter indicates. This can be demonstrated by a flight from Duluth, Minnesota to Fort Wayne, Indiana. Here we see that the horizontal pressure changes from 1024 millibars at Duluth to 1008 millibars at Fort Wayne. Looking at the vertical pressure pattern, the isobars would slope in this manner. On this proposed flight, if we flew a constant indicated altitude without correcting for the pressure changes en route, we would fly along an isobaric surface, and we would be flying lower than the altimeter indicated. In such cases, we should obtain a current altimeter setting and climb back to our proposed flight level. The reverse is of course true when flying into higher pressure areas. There are other altimeter errors which you will hear about in future instruction. The aviator should be familiar with the wind flow associated with pressure systems. The horizontal pressure gradient force is the primary force that causes wind to flow. With this force alone, the wind would flow quite predictably from the center of high pressure areas to low pressure centers. There are, however, other forces acting on wind flow that modify speed and direction. Among these are the Coriolis force and frictional force. The Coriolis force is an apparent deflective force brought about by the rotation of the Earth and does not change the wind speed. This apparent force causes a deflection of the wind to its right in the northern hemisphere. Wind produced by the pressure gradient force and Coriolis force alone will be parallel to straight isobars. The frictional force decreases the wind speed and in turn decreases the Coriolis force and changes the wind direction. The resultant wind flow in the lower 2,000 feet flows at an angle of approximately 30 degrees across the isobars from high pressure to low pressure. At and above 2,000 feet, the wind flow remains parallel to the isobars at the respective levels. A partial result of these forces near the surface is to cause the wind to flow across the isobars, out of highs. We call this divergence. As the wind diverges from a high pressure system, the air near the center sinks. The subsiding air is heated by compression. This dries the air near the center of the high, creating a sky usually free of clouds. Because of this, we generally associate good weather with higher pressures. In low pressure areas, the air flows inward and converges. As the wind flows into a low pressure system, the air rises to compensate for the convergence. As the air rises, it expands and cools due to decreasing pressure. This cooling may bring about saturation of the air and the formation of clouds. In turn, this frequently produces precipitation and instrument flying conditions. It has already been observed that we generally associate good weather with high pressure systems. Clear skies, however, pave the way for considerable cooling at night. You will learn later that this contributes to reduced surface visibilities by fog, haze, and smoke. High pressure systems may be called anticyclones. Conversely, low pressure systems may be called cyclones. This term cyclone is not to be confused with tornadoes or other severe storms. There are some pressure and wind phenomena that require special attention. Let us first consider the hurricane, one of nature's most awesome sights. It's a low-pressure system that develops over the water in low latitudes. As the air moves into this low and rises, clouds form, releasing latent heat energy. The low intensifies, resulting in more convergence, lift, condensation, and energy. It literally seems to feed upon itself as it gains momentum. Wind speeds vary from 75 to 150 miles per hour, and occasionally stronger. The devastating effects of a storm of this type are too well known to warrant comment. Tornadoes, the most violent type of storms, are frequently associated with intense cold fronts. At other times, they are found in the southeast quadrant of low-pressure areas or the northeast quadrant of hurricanes. Tornadoes are extremely intense, but highly localized low-pressure centers whose vicious intensity is an old story. They descend from clouds as swirling funnels. Their formation and development is not fully understood. Another phenomenon of particular interest to aviators flying at high altitudes is the jet stream, a meandering channel of high-velocity wind generally found between 15,000 and 40,000 feet. Its altitude varies along its course, which is usually west to east, though not always direct. In it, wind speeds of 150 to 200 miles per hour and even greater have been encountered. It is a terrific booster going east. Going west, avoid it. In this film, you have seen the construction of pressure systems and wind flow. These will be important to you for further study of air masses and frontal analysis, which determine the more definite weather conditions along the routes you fly.